Hi, I'm Maggie. qPCR is a common molecular biology technique, but choosing the right detection chemistry can be confusing. I want to clear up some of the confusion by reviewing the differences between the two most common types of detection, dye-based and probe-based qPCR. Let's start with dye-based qPCR. This method relies on the use of an intercalating dye that binds specifically to the minor groove of double-stranded DNA. These dyes have very low fluorescence when they are not bound to DNA, but exhibit high fluorescence when bound to DNA. A double-stranded DNA binding dye is included in the qPCR mix, and the fluorescence signal is measured after each amplification cycle. Because fluorescence signals of these dyes increase dramatically in the presence of double-stranded DNA, qPCR amplification can be detected and visualized as an increase in fluorescence signal. DNA binding dyes are easy to use, but the detection is not sequence-specific. To confirm amplification specificity, melt curve analysis is performed after amplification is complete. The reaction is heated slowly. When the double-stranded amplicon denatures, there is a sudden change in fluorescence. This melt temperature is a function of the amplicon sequence and length. As a result, melt curve analysis can be very useful in verifying the specificity of a reaction by giving us information on the number and size of amplicons present. In probe-based qPCR, primers are used in combination with a probe to detect the amplification product. The probe is synthesized with a fluorescent reporter covalently attached, and the fluorescence of this reporter changes as the qPCR product is formed. The most commonly used probe chemistry is the hydrolysis format. With hydrolysis probe chemistry, the probe is labeled with both a fluorescent reporter and a quencher molecule. In a reaction well prior to thermal cycling, the reporter and quencher are close to each other, leading to quenching of the fluorescent signal. But during the amplification reaction, the probe binds to template and gets degraded by Taq polymerase. Once the probe is degraded, the reporter and quencher molecules are no longer held in close proximity, and the fluorescent signal can now be detected. The amount of fluorescence generated is proportional to the amount of qPCR products produced. With probe-based chemistry, you also have the potential to perform multiplex qPCR, using probes that are labeled with different fluorescent reporter dyes. This allows you to increase throughput and reduce variability by amplifying a gene of interest and a reference gene in the same well. Deciding which detection method is best for you is a matter of weighing which features are most important for your particular assay. To learn more about Promega's systems for real-time PCR detection, please visit promega.com/qPCR talk.